Welcome back to the deep dive. So last time we introduced this high-level idea of Kubernetes. We called it the Helmsman that manages containers at, well, just an incredible scale.
We really just painted the broad strokes.
Exactly. We covered what it does. But today we have a much more ambitious mission for you. We are popping the hood. We're opening up the engine block.
That's right. And this mission is, it's crucial. If you really want to move past the concept, you have to understand the anatomy of a Kubernetes cluster, the actual non-negotiable parts that make it all work.
So this isn't just naming components.
Oh, no. It's about understanding their function, and maybe more importantly, the why, the engineering reason behind each piece.
And we're going to stick with our analogy, right? The two big pillars. We've got the control plane, which we can think of as the sophisticated brain of the whole operation.
Making all the big decisions.
And then we have the worker nodes. That's the muscle. That's where all the actual work gets done. So the plan is to identify every key component in both of those buckets and really dig in.
Exactly. And let's start with the control plane. Honestly, if you can get your head around these 4 or 5 components, you understand the whole architecture. This is where the state, the memory, all of it, this is where it lives.
Okay, let's unpack it. If it's the brain, what's the absolute front door? The one point of entry for every single command.
That would be the Kube server. If Kubernetes has a center of the universe, this is it.
I always thought of it as the ultimate gatekeeper, like the front desk at a hotel.
That's a great way to put it.
Is it really true that nothing happens in the cluster unless this component says so?
Absolutely.
Yeah.
It's the only component that communicates with everything else. It doesn't matter if it's you submitting a new application or a worker node reporting its health.
Or even internal components talking to each other.
Yep, all of it. It all goes through the API server. It handles authentication, validation. It makes sure every request is legitimate before anything else can happen.
Okay, but if it's the central hub for literally everything, that sounds like a huge potential bottleneck, right? We're talking about massive scale. How does it not just fall over?
That's a fantastic question. And the architectural answer is, well, it's pretty elegant. The API server is designed to be horizontally scalable. And the reason it can do that is because it is completely stateless.
Stateless, so it doesn't remember anything on its own?
Not long term, no. It just processes requests, checks them against the cluster state, and then moves them on. It doesn't hold the memory itself. That means you can run multiple copies, multiple replicas of the API server, and they all work just fine because they're all looking at an external source of truth for the data.
Ah, okay, so that's the key. If the API server is just processing the flow, then we need that other component, the one that acts as the cluster's permanent memory. Where does Kubernetes write everything down?
That would be etc., spelled etcd. That is the cluster's single definitive source of truth. It's a distributed key value store, a database, and it holds everything. The configuration, the current state, the desired state, all of it.
The source material really hammers home how high stakes this one component is. What does that actually mean, having a single source of truth like this?
It means it is the most critical piece of the entire puzzle. Think about it like this. If you can save your etc. to data, you can literally delete everything else, the API servers, all the worker nodes, and you can restore the entire cluster to its exact previous state from that backup.
Wow.
But the flip side is also true. If you lose etc., you lose the cluster. It's gone. You lose its identity. You lose everything.
So if it's that critical, how do you keep etc. itself from failing? We're talking about high availability for the cluster's actual memory.
Right. And this is where we get into some really cool engineering. So etc. guarantees its own consistency and fault tolerance using something called the Raft consensus algorithm.
Raft?
Yeah. It's designed specifically to keep data consistent across the cluster of machines, even if 1 or 2 of those machines fail. And this is why you absolutely must run etc. on an odd number of nodes, usually 3 or 5.
Wait, why an odd number? Is that just a convention?
No, it's fundamental to how it works. It's for quorum. To make a decision to write data, you need a simple majority to agree. With 3 nodes, you need 2 to agree. With 5, you need 3.
Ah, I see. So if you had an even number, say 4, and 2 failed.
The remaining 2 couldn't form a majority. They'd be deadlocked. The cluster would grind to a halt. So that ability to always guarantee a majority, even with failures, is the whole architectural reason why etc. is the right choice here.
That's fascinating. Okay, so the API server gets the order, validates it, etc., writes it down permanently in this fault-tolerant way. Now we know what we want. But who decides where the work actually runs?
Now we move from those foundational pieces to let's call them the dedicated decision makers.
Yeah,
And that starts with the kube scheduler.
the matchmaker. Or the travel agent, I think you called it. Its job is purely about resource placement, isn't it?
That's its entire world. A new pod is requested. The scheduler looks at what that pod needs, scans every available worker node, and finds the absolute best home for it. Then it just tells the API server, I've made my decision. The pod doesn't get a say. The scheduler just points and says, you go there.
Okay, the source had a simple example like a pod needs 4 gigs of RAM and it finds a node with 8. But that feels too simple for a deep dive. What's actually happening under the hood? How does it make that choice?
It's a two-phase process,
Yeah.
and this is what makes it so smart. The first phase is filtering. The second is scoring.
Okay.
So first, it runs a series of what are called predicates. These are just yes or no questions. Does this node have enough RAM? Yes or no? Does it meet the security policy? Yes or no? Is the node tainted in a way that repels this pod? Any node that gets a no is immediately filtered out of the running.
So that first step just gets rid of all the impossible options.
Exactly. Then, for all the nodes that are left, it moves to the second phase, priorities. This is the scoring part. It runs a bunch of algorithms to rank the remaining nodes. It might prioritize nodes that have more free space to avoid fragmentation, or it might try to spread pods across different physical racks for high availability.
And the node with the highest score wins.
The node with the highest score wins the assignment. And that two-step complexity, that's what makes Kubernetes a true orchestrator, not just a simple task runner.
That makes so much more sense. Okay, we have the gatekeeper, the memory, and the matchmaker. But now, let's talk about the magic. The real selling point of Kubernetes is its self-healing. A node fails, it fixes it. A container dies, it brings it back. What component is doing that work?
That massive job falls to the Kube controller manager. This component is the real unsung hero of the cluster. It's the engine of resilience. It's the fixer.
I like that, the fixer, but what's the actual mechanism? How does it fix things?
It all comes down to one core architectural principle, the continuous reconciliation loop. Inside the controller manager, there are dozens of smaller controllers, node controller, replication controller, and so on.
And they each have their own domain.
Exactly. And they all follow the exact same pattern. 1, observe the current state of the cluster. 2, compare it to the desired state that's written down, and etc. And 3, if there's a difference, act to make the current state match the desired state.
So it's not just executing tasks, it's constantly fighting against any drift from the plan.
Constantly. If your desired state says, I want 3 replicas of my app, that's what's in etc. The replica skit controller is always watching. If it sees only 2 are running, that's a mismatch. So it immediately acts. It tells the API server, hey, we need 1 more pod, and that loop runs forever.
And what about when a whole node goes down?
That's the node controller. It sees a node has stopped reporting in, it waits for a specific timeout, then it declares that node dead. And then it starts reassigning all of that dead node's work to healthy nodes in the cluster. That's the self-healing in action.
That really solidifies the control plane. It's the brain trust. Reception, memory, strategy, and self-correction. Okay, let's switch gears to the worker nodes. The muscle, where the containers actually live. What's the one agent that has to be on every single one of those machines?
That would be the kubelet. It must run on every single worker node. It's the primary node agent, the main liaison back to the control plane.
So if the worker node is a construction site, the kubelet is the foreman.
Perfect analogy.
Yeah.
Its very first job is to register that node with the control plane. It calls up the API server and says, hey, I'm here. I've got this much CPU, this much RAM. I'm ready for work.
And then it waits for orders.
It waits for orders. And when the scheduler makes its decision and assigns a pod to that node, the kubelet is the one on the ground that makes it happen. It takes that instruction from the API server and makes sure the pod's definition is enforced locally.
So the scheduler points and the kubelet builds.
Well, this is where a really important technical detail comes in. The kubelet, our foreman, doesn't actually know how to build a container. It knows what to build, but not the nuts and bolts of it. For that, it delegates the heavy lifting to a specialist.
And that's the container runtime.
The container runtime, the engine. And, we all think of Docker, but the sources point out that Kubernetes has moved on from that being a requirement.
Right. So what's the standard now?
The standard is an interface. It's called the Container Runtime Interface, or CRI. This was a huge deal for the ecosystem. The kubelet just speaks to the CRI. And any runtime that understands that interface can be plugged in underneath. It could be containered or something like CRO, which was built specifically for this.
So the CRI is like a universal translator. The kubelet doesn't care what engine is being used as long as it speaks CRI.
You've got it. The kubelet just issues a command like spin up this container image with this specification, and the runtime handles all the low-level stuff, pulling the image, setting up the namespaces and C groups. It completely decouples the orchestration from the specific container technology.
Yeah.
Huge flexibility.
Okay, so the kubelet enforces the order, the runtime builds the container, the work is now running. But how does network traffic from the outside world find the right pod on that machine?
That is the job of the final core component on our worker node, Kube-proxy.
The traffic cop.
Exactly. Now, a lot of people hear proxy and they get the wrong idea. It's not like a web proxy. We have to dispel that myth.
Okay, so what does it do?
Kube-proxy runs on every single worker node, and its job is to manage the networking rules on that machine itself, usually by manipulating the kernel's IPTables or IPVs rules.
So it's like the node's own personal network administrator.
That's a great way to think about it. It watches the API server for changes to things called services, which are how you expose an application. And it translates those abstract definitions into concrete low-level firewall rules. So when a network packet arrives at the node for a specific service, the kernel already knows exactly how to forward it to the correct pod's IP address.
Even if that pod just got created or moved.
Even then, it keeps everything in sync.
This has been incredibly clarifying. I think it's time to lock this in with a synthesized review for you, the listeners.
Let's do it. Let's tie the names directly to the roles we've been talking about.
Okay. In the control plane, the brain making the strategic decisions we have. The API server, that's the front door. It's stateless and validates everything. Then, etc. The memory, the single source of truth using the Raft algorithm.
Right. Then the kube scheduler, our matchmaker, using its filtering and scoring phases to place workloads. And finally, the kube controller manager, the fixer, running those constant reconciliation loops to make sure reality matches the plan.
Perfect. And down on the worker nodes, the muscle where the work gets done, we have the kubelet, the foreman, the local agent taking orders and enforcing them.
And the kubelet directs the container runtime, the engine, which speaks the CRI standard, to actually build and run the containers.
Yeah.
And last, the Kube-proxy, our traffic cop, managing the local network rules so everything can communicate.
You know, it is complex, no doubt, but when you break it down by those roles, brain versus muscle, and you understand the why behind things like, et cetera, it's consensus or the scheduler's phases, the whole system just feels so logical.
It really does. So we've established what the parts are, but before we wrap up, I want you, the listener, to really reflect on what I think is the most revolutionary idea in all of this.
Okay, give us that final thought.
Think about that controller manager again, that reconciliation loop. Most systems, most traditional IT, is built to execute a command. You say, do this, and if it fails or the system changes over time, a human has to step in and fix it.
Right, the classic pager alert at 3 a.m.
Exactly. Kubernetes is built on a fundamentally different premise. It is designed from its very core to be in a continuous state of self-correction. It is always trying to get back to that ideal state defined in these world, etc. And that shift in thinking from one-time execution to constant reconciliation, that is what makes Kubernetes so resilient, so autonomous, and frankly, why it's the architecture defining modern cloud computing.
That continuous autonomous self-correction, that really is the magic that lets the helmsman sail so smoothly. This has been an incredible look under the hood. Thank you.
My pleasure. Hopefully you'll never look at a running pod the same way again.
And thank you for joining us for this deep dive. We'll be back next time as we continue our exploration of this crucial architecture.